change the thing. So let me go over and do that. Hello, everybody. I guess this will also bring up the comments in case somebody starts chatifying the place. All right. We'll call this duction because I'm grabbing the root. I'm grabbing the root. Induction and deduction. Right. So I watched Ken Ham and Bill Nye, and it relates to this kind of thing of, hey, how do you know it if you can't see it? You didn't see historical science is where they're trying to extrapolate into the past, and they can't see, what happened, and therefore it's just religion to believe that it couldn't have been God, and so on and so forth. Ken Hammy kind of stuff. So I'm grabbing the root duction. I believe that this concept of duction has to do with a belief in a continuity, or another way of putting it is a similarity between things, a relationship, an intimacy, if you will, between things that are located close to each other in time or space, or especially time and space, right? And so you have induction and deduction. Now I'm grabbing the root duction because I think there's other ways of splitting these things up, but these are valid categories which are complete. Various kinds of duction, whatever they may be varied, as I believe, you can categorize them as inductive or deductive. Right? That is a net that captures all kinds of duction, even if there's other ways to characterize them. So induction is like, let's say I measure your height at 2 times in your life. And at one point I measure that you're 2 feet tall, and another time, lo and behold, you're 4 feet tall. Deduction is the inference rules by which I would assume and be able to presume and know that at some time in between you were 3 feet tall. There's no skipping. There's no going from 2 straight to 4. You have to go through 3. That is deduction. Induction would be the rule by which I go, wow, at this age, at this time, 2 feet tall, at this time, 4 feet tall. Hey, at a future time, 6 feet tall. So right away, that characterizes it. Now, you do have to make these kinds of future predictions, and also it's the same thing if you go back in time. If you go outside the time limit of your data, that's different than making inferences about what happened between the 2 times. Okay. But obviously, deduction, that you had to go through the 3-foot point, is more solid, more reliable. It's traditionally considered more reliable, and it is more reliable, and scientists consider it more reliable than this idea of, oh, look, I've seen the trend, and going outside inductively to future cases based on the cases you've seen, because that person might only end up being 5'10". Maybe they never reach 6 foot tall, right? And these induction and deduction are analogous. They have a great analog in math of being interpolation for induction and extrapolation for induction. Wait, did I do that wrong? Yeah. You try again. Interpolation is deduction, and extrapolation is inductive. Okay, so for example, let's say I have these points of data, and on the x-axis is time. It is to extrapolate to say what happens at point 7. That's extrapolation. If I was to say what happens at 1.72, between the dots. If I tried to figure out what the dots are between the dots, the red dots are the data we've taken, we've seen, we've sensed directly. Because the question is, how do we know things beyond what we've sensed directly? That goes back to the Ken Ham thing. That's the ploy he always uses. Oh, you didn't sense it directly, therefore you're just basing it on a belief that of how to extrapolate, and therefore I can choose the Bible for that. To say what's out there at 7, you have to use induction. You have to extrapolate. Right. So for interpolation is an interesting thing. Let's say that I have these data points here. I want to figure out what the other data points inside, in between the red dots are. Right. So one thing we do in this case is just draw lines between them. That's called a linear interpolation. Then I presume that this point here, at point 5, x equals 0.5. Well, it's right here. It's on the straight line between the 2 points that I know. But of course, we also know that's probably a curve, so the linear interpolation is not most likely. And again, it's because of the deduction that we think things are continuous, or at least if they're discrete, that neighbors will have similar values, that we don't expect this abrupt change in slope right at this point. It's probably going to curve in between. So we have mathematical techniques to have better, smoother ways of fitting this. And in science, the main one is a polynomial. So this is where it's put in form of an equation of y equals, x to the n plus x to the n minus 1, and so on and so forth down to the constant at the end. So you have x squared plus blah blah blah, or you have x to the fourth plus x to the third plus x to, with coefficients there, and you can fit any. It's been proven you can fit any dots if you have enough terms in your polynomial. Or if we just want it to look pretty, we can use a spline. You notice those are very similar. And a spline is just using a subset of points on 3 or 4 points in order to make that part of the curve. And it's guaranteed to smoothly fit this next guy, because you move 1 point down and then you keep using the sets of points to just draw this nice curve which weaves around and hits everything quite smoothly without the disjointedness. That's interpolation. But then if I get this kind of a curve, I can extend it, especially let's say I decide, oh, that's like a sine, and so I fit a sine wave to that. I find a sine wave that goes through those points, and then when I want to go to 7, I say, oh, it's going to be here according to that. And then that would be inductive, essentially. And really, this is how everything works, based on our sense data, or even if you want to break down what goes on inside the mind. And these are like the specifications of what you have to argue. You have to know where your data points are, and then you have to consciously know if you're trying to state something between your data points or outside your data points. And they're both legitimate, because here's the thing too, induction and deduction, they actually have more similarities than our common sense understanding would have it. So especially when observing the past. When you're observing the past, induction has characteristics more like deduction, right? Telling the future, it has an emotionally different feel to it. But it seems very similar in terms of deduction as trying to zero in on what happened in the past. You can't observe the past, but you can induce into the past. So if for example, let's say a man was in a room, you see the man in the room, that's your data point. You can induce that he must have come into the room at some point. He came into the room, right? If a detective goes to a house and sees stuff's been stolen, then he can induce somebody was in the room, the person that left with the stuff. and and they got into the room somehow, and he'll look around. Oh, they got in through the window. And that kind of induction is, pretty much should share the category of reliability that a deduction has. Because with deduction, you have similar problems with induction, which is, when you're assuming the lines are straight, well, that's not true. You can't tell what was there. You're trying to make an educated guess. Now, if you choose the line, and it's supposed to be out here, and you're guessing in here, you're only going to be a little bit off. So better curves will improve, your results overall, but maybe not. Sometimes this could be it is going up linearly, and then the machine went in a different thing, and then it did go linearly. In that case, making a fancy curve would actually make your results worse. So these are the kinds of noise that you have to deal with. But you can characterize these things, and you can reduce the noise below the signal, and you can, solve a crime. You can read the ages of stones based on the physical processes. You're always just dealing with data that you've collected at particular points of time. And in the study of geology and evolution and so on, many of those points in time are going to be before any data that you have directly that you have from the time. There's no observations from 100 million years ago. You have to look at the current data, but based on watching, like for example, the decay of elements into other or isotopes into other isotopes, we have seen that. We can measure, what the pattern is. Is it a sine wave? Is it, exponential? Is it, what is it? And we can extrapolate, which is induction back in time in this case that I'm describing, and come up with um, guesses that are within some margin of error, right? So, and we can calculate that margin of error. And so, this is why to have a scientific theory also, uh, postscript, is this is why you have to take data. Your scientific theory cannot be judged based on, doesn't this make more sense and wouldn't it maybe work? Hey, there's friction, but the thing gets skinnier. The friction doesn't go to zero, but you see how it go down. So maybe it's zero. Maybe you can ignore it. Well, none of that matters. You need to take the data. You have to have the points in order to do a deduction, induction, or any kind of ductive process. Duct means a thing that contains a flow and directs a flow, and it's the flow of information that we're talking about. So I'm sure that'll clear that up for Ken Ham and Gary and Mendham.